Let's learn about graphing exponential functions. While most puns make me feel numb, mathematics puns make me feel number. On the agenda, we're going to determine if a model is growth or decay, graph the parent function along with its transformations. We'll do percent increase and decrease problems. We'll write them, graph them, and evaluate the models. Let's get ready. You're going to need your notebook, pencil, and calculator. And just taking a look at these two, we have COVID cases on the left. You can see that it is increasing. And then on the right, they bought a caravan at 20,000, and it is what we call depreciating or decaying. We're going to start by graphing the parent, and I picked a base of 2 here. And when we don't know the shape, a table of values is a good idea. So I picked my x values between -3 and 3. So when I plug in y equals 2 to the -3, remember a negative exponent means reciprocal. So this is going to become 1 over 2 to the 3, or 1/8. We'll have 1/4, 1/2, 2 to the 0. Remember, anything to the 0 is 1. And then we have 2 to the 1, 2, 4, and 8. When we go ahead and graph those, and then 1, 2, and then 2, 4, we're going to get an exponential curve that is a growth. We can ask ourselves, if I kept putting more negative x's, -5, -6, will this ever reach 0? No. Will it ever go below 0? No. So this is an example where we are going to have a horizontal asymptote at y equals 0, the parent graph. We have an intercept, a y-intercept of 0, 1. That's our parent graph. We call it a growth. I changed the base to 1/2. I have the same x values. So now if we think of 1/2 to the -3, it is a reciprocal, so it becomes 2 to the 3. So we have 8, 4, 2, 1, same y-intercept, 1/2, 1/4, 1/8. So -2, 4, I'm going to graph these. And same thing, but this is now a decay. So we're going to do an exponential curve that is falling. It still has the same y-intercept of 0, 1. It still has the same horizontal asymptote of y equals 0. It's just getting smaller each time and approaching 0. Make sure when you graph it, whether it's on Desmos or on your calculator, you realize that the graph is never going to touch 0 here. It's approaching it, but it doesn't touch. It looks like it touches, though. So let's look at what happens when we put some more letters in, and we're going to graph the transformation. So we have A, B, H, and K. So A has a lot of power. It's going to be our starting y-intercept. We're going to start there. It's not like a parabola that has a vertex that we're going to move, but that's the point that we're going to move. If A is negative, it's going to be reflected over x. If A is greater than 1, it's vertically stretched. And if A is between 0 and 1, it's vertically compressed. B. So B is the base. It comes from the ratio. If I had a table of values, it's y2 divided by y1. It's also going to determine if it's growth or decay. If B is greater than 1, it's going to be a growth. And if B is between 0 and 1, it's going to be a decay. H, as always, with my x and my exponent, is going to move it left or right, and it's going to move opposite. And then K is going to move it up or down. Also, another thing that x and the exponent is going to do is if x is negative, it's going to reflect it over y. So when I have, say, a growth, but then I have y equals 2 to the -x, that's going to reflect it over y, and it's going to look like that, which means it's going to look like a decay, but it's actually the reflection of a growth. I just wanted to share with you what happens when you change the base. So you can see I increased all the way to 100. They still have that same y-intercept. They still have that same asymptote. Let's jump in and we'll try to graph some transformations. So looking at all these numbers, I need to figure out what the 3, 2, 4, and -5 do. I'm going to start by describing the shifts, and I'm going to start with the 2. The 2 means that it's growth. So we're going to keep that in mind. Then I'm going to go to the 3. It's vertically stretched by 3, but I'm also going to start at y equals 3 for my y-intercept. It's not going to be my actual y-intercept, but that's a place I'm going to start. That's the point that I'm going to then move left 4 and down 5. The down 5 is going to tell me my horizontal asymptote, y equals -5. So I'm going to plot that because that's going to help me make sure my graph is in the correct spot. So from this original point of 0, 3, I'm going to move left 4 and down 5. And I have a point right there. So that point is -4, -2. Notice I'm putting it in the middle of my table. I'm going to ask you to plot 3 points. So according to the x, I'm going to go a little bit smaller and a little bit bigger to find the points around that. So when I plug in a -5, I'm going to get 2 to the -1, which is 1/2. 3 times 1/2 is 3/2. 3/2 minus 5 is -3.5. So -5, -3.5. And when I plug in -3 plus 4 is 1, so that becomes 6 minus 5, which is 1. -3, +1. And we can connect that for a curve. My domain is going to be all real numbers, so infinity in interval notation. My range does not include the -5, so that's a soft bracket to infinity. Here I just want to show you on Desmos a little clearer. This was our starting. We started at 0, 3, and then we moved it over 4, down 5. Let's try this one. I notice my base is 1/5, so this should be a decay, but then I also see that this is going to be reflected over x. I am going to start at 2, not -2, start at 2. So I'm going to go to 2 and put a point. Then I'm going to go left 2 and up 3. The up 3 is going to tell me that my horizontal asymptote is y equals 3. So I'm going to dot that in because that's not going to change, but it's going to be important with my reflection. So I'm starting at 2. I'm going to go left 2 and up 3. And I have a point there. It is not an actual point on my graph because remember, we still have to reflect it. I save the reflection for the end. So this point is 2 away from my asymptote, which means this is like an ink blot. If I were to fold it on that dotted line and bend it over, it would end up being right here, which is also 2 away. So this point is an actual point on my graph. I am going to erase that one so we don't get that confused. So I am at the point -2, +1. If I plug it in and check, that's going to give that 0. 1/5 to the 0 is 1. -2 plus 3 is 1. So that's correct point. Then I'm going to pick -3 and -1 to work with. So -3 would be a -1. 5 to the -1 is 1. Is 5. Oh, sorry. 1/5 to the -1 is 5. 5 times -2 is -10. Plus 3 is -7. So we're way down here. And then plugging in -1 plus 2 is 1. So -2/5 plus 3 is 2 3/5. -1, 2 3/5, somewhat up there. So that looks very different. But remember, it would have been like that somewhat, and then we would have reflected it. My domain is all real numbers, and my range is -infinity to 3. I wanted to show you on Desmos again just to have it a little bit clearer. This is the point that is 2 away from my asymptote, so when I reflect it, it also has to be 2 away, and that's my final graph. Let's look at an application. We can do percent increase and decrease types of problems. So we have this model, a of t equals a times parentheses 1 plus or minus r, all raised to the t. It is not like quadratic formula. You do not keep both the plus and minus. You have to decide what to use. So the capital A is your final amount. The little a is your initial amount, what you start with. So how much money are you putting into the bank, or how much milliliters or milligrams do you have to start with? The positive is the increase or appreciate, and the negative is if you are decreasing or depreciate. For the rate, make sure you change it to a decimal. So if it was 5%, you're going to be using 0.05, and then t is the time period. Things that appreciate, houses usually, works of art, valuables. Things that depreciate, often cars do, radioactive elements. Here's our example. You invested $1,000 in a savings account at the end of 6th grade. The account pays 5% annual interest. How much money will you have in your account after 6 years? We're asked to write the model and then use the model to make a prediction. So the $1,000 is what I'm starting with. How much money will I have at the end? So I don't know A of t. Well, that's good. That means I'm going to know everything over here. So I have 1,000, 1 plus, because it's increasing, 0.05. I changed my rate to a decimal, and then I'm putting it in for 6 years. If you have everything on the right-hand side, you can just pick up your calculator, and after 6 years, you will have $1,340. You want to make sure that makes sense. You put $1,000 in 6 years, you could have about $1,300. So that one is finished. Here we have a population of 120,000. It's growing, which means we're going to do plus 1.2%. We have to change that rate. After how many years will the population be over 180,000? How many years? That means we don't know our t. So this one's going to be a little bit different. Well, I'm ending at the 180,000, starting at 120,000. 1 plus 0.012 to the t. So there's our model. You cannot multiply in the 120,000 because that would be doing multiplication before your exponent. I'm trying to get to this t, so algebraically I could divide by the 120,000. And that's going to give me 1.5 equals 1.012t. It's still an exponential equation. We're just beginning, so we don't quite know how to solve this algebraically. So we're going to graph. And I would like you to graph y equals 1.5, the left side, and y equals 1.012t, the right side. The 1.5, that's going to be your horizontal, and then you should see very steady growth. We're looking for that point of intersection, so I'm going to let you figure out how you have to adjust your window to find that. You want to do second trace and then go down to intersect. So second, trace, intersect. Put it on the left side first, and this way I put it on the line, and then put it on the right side, and then hit enter. So left, right, enter. And you should get about 34 years. In 34 years, you'll have about 180,000 people. So to recap, we're going to use transformations in a table to find some more points of our exponential graphs. We have the percent increase and decrease model where we'll write a model and either solve it algebraically or graphically. Good job.